All right, let's dive right into this explainer and turn some pretty dense engineering codes into a practical end-to-end field guide for curtain wall design. Whether you're an engineer crunching the numbers or part of a site team actually bolting these massive panels to a skyscraper, you know that keeping a lightweight glass wall attached to a building is no small feat. So today, we're building the ultimate master checklist for you to follow for every single component.
Well, it all starts with understanding our invisible enemy. Wind is a dynamic, constantly fluctuating force. You see, unlike the heavy concrete and steel of the primary building frame, which are mostly just fighting gravity, a curtain wall is basically a giant sail. Because it's this huge, lightweight, and incredibly flexible surface directly exposed to the elements, wind pressure, not dead load, is almost always the governing structural design load we have to beat.
So here is our 5-point master checklist for safe curtain wall design. First, calculating the wind load. Second, tracing the load path. Third, looking at framing, where deflection trumps strength. Fourth, verifying profiles, gaskets, and fixings. And finally, fifth, safely sizing and insulating the glass.
Let's kick things off with check 1, calculating the wind load.
Using the Indian standard IS 875 Part 3 code as our reference, we figure out the wind load through a very specific 3-step progression. Step 1, we grab the basic wind speed of the region. But obviously, a building in a dense city center experiences totally different wind than one on an open coastline, right? So Step 2 modifies that basic speed into a design wind speed, factoring in the terrain, the structure's lifespan, and local topography. Finally, Step 3 uses a standard formula, 0.6 times the velocity squared, to convert that regional weather data into a static design wind pressure that we can actually engineer against.
But here's something absolutely crucial about how wind actually behaves. It doesn't just push against the front of the building, it accelerates around the sides and whips over the roof. This means building corners and top floors act like giant suction cups. If you're an engineer or a site inspector, you absolutely must ensure that these corner and edge zones get totally separate, far more rigorous design checks than the typical field panels in the center. Let's put some real numbers to this to see what I mean. Take a typical 30-meter commercial building in Mumbai. Our calculations show that while the normal center field of the facade might experience a pressure of 1.04 kilopascals, the intense suction at the corners jumps to 1.66 kilopascals. If a site team blindly installs standard field-rated brackets at those corners, that massive suction force could literally rip the unprepared panels right off the building. No joke.
All right, moving right along to check 2, tracing the load path.
Now that we know the raw force of the wind, we need to trace exactly how that load travels through the facade and safely into the foundation. Every single person on site needs to understand this chain of custody. It goes like this. The wind hits the glass. The glass transfers that pressure to the rubber gasket. The gasket pushes into the horizontal and vertical aluminum mullions. The mullions transfer the load to the steel brackets, and finally, those brackets anchor the whole shebang into the concrete floor slab. If even one link in this chain snaps, the system fails.
And along this path, it's not just about raw strength. Serviceability is key. Site teams and engineers have to verify these exact deflection limits. For a standard aluminum mullion, industry practice limits bending to the length divided by 175, or a strict maximum of 19 millimeters. Why so tight? Well, if that frame flexes more than 19 millimeters under a heavy gust, the brittle glass inside it could crack, or the gaskets might lose their weather-tight seal and literally just let the rain pour right in.
Okay, check 3. Framing, where it's all about deflection over strength.
Once our wind pressure becomes a distributed line load across the surface, we fall back on standard, tried-and-true beam formulas. We treat the vertical mullion just like a simply supported beam spanning from one floor slab to the next. Engineers calculate the maximum bending moment and the maximum shear force to make absolutely sure the selected aluminum profile is robust enough to carry the load without snapping.
But here's the kicker. Aluminum has a much lower modulus of elasticity compared to steel. It's roughly 1/3 as stiff, meaning it's incredibly flexible. So stiffness, rather than raw strength, dictates our entire design. An aluminum mullion is almost always going to bend too far long before it actually breaks. This is exactly why in high-rise construction, engineers vastly prefer deeper, boxier profiles. A deeper box dramatically increases the moment of inertia, giving us the stiffness we need to stay safely under that 19 millimeter limit.
Let's look at check 4, profiles, gaskets, and fixings.
Zooming in on the hardware, you'll see curtain walls definitely don't use off-the-shelf pipes.
Engineers select highly customized aluminum extrusions optimized for multiple jobs at once. Not only are they shaped for that stiffness we just talked about, but they feature complex internal geometries. We're talking built-in drainage channels to weep out any trapped water. And you see that little polyamide strip? That is a thermal break. It literally separates the outside aluminum from the inside aluminum, stopping heat transfer in its tracks.
Now listen up if you're on site, because this next part is a massive red flag checklist item. The brackets connecting the mullion to the slab are not all the same. You absolutely must verify that every floor-to-floor mullion run correctly pairs exactly one fixed-point bracket with multiple sliding point brackets. The fixed bracket carries the heavy dead weight of the system. The sliding brackets, on the other hand, have slatted holes. These allow the mullion to slide up and down as the aluminum expands in the hot sun, while still locking in the horizontal wind load. If a crew accidentally bolts a sliding bracket perfectly tight, the building can't naturally flex, and the framing will literally buckle under thermal stress.
And that brings us to our final stop, check 5, sizing and insulating the glass.
Glass is the most visible, yet arguably the most fragile part of the system. Because it's a brittle material with what we call probabilistic failure behavior, meaning it fails based on microscopic statistical flaws rather than just yielding like metal, we can't use simple beam theory. Instead, engineers rely on the ASTM E1300 standard. They take specific, non-factored load charts based on the panel's exact size and multiply that by a glass type factor. For example, bumping up from standard annealed glass to fully tempered glass multiplies its resistance by 4. This ensures our load resistance safely exceeds the design wind pressure.
But getting the glass strong enough isn't the whole job. We also have to minimize heat transfer, measured as the U value. Upgrading from a simple 6mm single pane down to a double or triple glazed unit with a low E coating and argon gas can drastically cut that U value down, from a pretty poor 5.8 all the way down to a super efficient 0.6. For a massive glass skyscraper, checking this box translates to enormous savings in cooling energy.
So bringing it all together, here is your ultimate end-to-end master checklist. Whether you're in the office modeling loads or on a scaffold inspecting bolts, this is your roadmap to structural integrity. Calculate the exact wind pressure, and don't forget the corner suction. Verify every single link in the load path. Ensure your aluminum mullions are stiff enough to meet those deflection limits. Rigorously check that fixed and sliding brackets are placed correctly. And finally, size the glass using probabilistic charts while keeping thermal performance in mind.
But as we wrap up this explainer, I want to leave you with one final, kind of sobering thought. The engineering codes we rely on today are fundamentally based on historical weather data. But as climate change intensifies and baseline wind speeds increase across the globe, it really makes you wonder, just how much stronger are our facades going to need to be in the decades to come? Will future superstorms force us to completely rewrite these master checklists from scratch? Let that sink in as you head back out to the site or back to the drawing board.